Welcome back. We were discussing properties of integrals, abstract integrals. So, all the properties of abstract integrals are proved in exactly the same way. You prove it for simple functions first, then you prove the property for non-negative measurable functions, and then you generalize for any measurable function. Okay. So, that is the way all results are proved, regard all properties of integrals are proved. Okay. So, we were in the middle of discussing a number of properties. So, I think we were discussing property number 6, which said that if g is non-negative and integral g d mu equals 0 equal to 0, then g equals 0 mu almost everywhere, right. This is the property we were discussing. So, the proof of this is as follows. Assume the contrary. Let B be the set where g of omega is strictly bigger than 0, right, and assume mu b is. So, you want to prove that mu b is 0, right. To get a contradiction, you assume that mu b is not 0, that it is strictly positive. Okay. Now, you want to show that this leads to a contradiction, right. So, then we defined, let B n be defined as the set of all omegas for which g of omega is greater than 1 over n, right. This is what we defined, correct. Good. Now, we also know that B n's are nested increasing or nested decreasing. Nested B n is contained in, is that correct? Correct. And so, we have and union I equals 1 through infinity B n is equal to B, right. We are saying that this set is equal to that set. In order to show this, you have to show that this is contained in this and this is contained in this. So, one way containment, the containment in that direction is very easy, right, because if you are contained in any of the B n's, it is immediately clear that g of omega is greater than 1 by n, therefore, g of omega is bigger than 0. But on the other hand, if you want to show the containment that way, that B is contained in this, for you take any omega for which g of omega is bigger than 0, then there exists a k for which g of omega is bigger than 1 by k. So, there exists a k for which omega is in B k, therefore, it belongs to the union. So, these two sets are equal. Okay. Then we used, then what we said is we can use continuity of measures, right. So, we said mu b is equal to limit n tending to infinity mu of. So, this is mu of the measure of that is equal to, I must actually write B I, is it not? Yeah. So, the measure of that is equal to limit n tending to infinity mu of B n, right. This is the continuity theorem for measures for nested increasing sets, right, mu B n. Is that fine? All right. So, this is an important relation. So, we have assumed that mu b is strictly positive. So, we have written a strictly positive mu b in terms of a limit of a sequence mu b n, right, which means that for all n greater than some n naught, mu b n should remain positive, correct. So, you are approaching a positive number, right, this limit is a positive number you have assumed. So, this guy, the sequence must be positive for all n greater than some n naught, correct, agreed. So, actually all this we need is there exists, thus there exists k such that mu b k is strictly positive, right. This has to be the case. Thus, integral g d mu will be at least as big as, see, integral g d mu is the supremum of is the supremum of simple functions, the integral of supremum of the integral of simple functions. One such function would be to say that, see, the function 1 over k over b k, right, will have this property, right, it's definitely smaller than g, correct, by definition. So, you will clearly have that g integral g d mu will be bigger than or equal to 1 over k times mu b k, correct. Got that? Because this is a supremum of all simple, this is a supremum of the integral of simple functions, right. An example of a simple function which is less than or equal to g is the function which takes the value 1 by k over the set mu b k, or the set b k rather, correct with me, because over the set b k g of omega is bigger than 1 by k, correct. So, the function 1 by k, the function which is constant at 1 by k over the set b k is a lower bound, is a simple function which is a lower bound on g. So, this must hold. Now, what do you know about that guy? No, this is bigger than 0, right. Yeah. So, you take that k, right. So, and this is a contradiction. Why is it a contradiction? It violates this, right. So, this assumption must be wrong. So, mu b equal to 0, okay. Are there any questions on this proof? So, in particular for a non-negative random variable, if expectation of x is 0, then x is equal to 0 almost surely, right. Property number 7. Property number 7 is a very fundamental property of integrals called linearity. Integral g plus h d mu is equal to integral g d mu plus integral h d mu. Okay. So, this is the integral form of the statement. If you want to state it for a random variable, what will it look like? Expectation of x plus y, right, expectation of x plus y is equal to expectation of x plus expectation of y. This is always true. This is a very fundamental property. The integrals are linear operators on functions. Okay. So, linearity includes this, but the next one I am going to say is also is a scaling. So, you integrate integral a g d mu will be a integral g d mu. So, put together it is linearity, all right. Alright. So, the proving this, so again right, this is true for any measurable functions g and h as long as all the integrals are well defined, alright. But as usual the way you prove it is you first prove it for simple functions. Can you prove this for simple functions? If g and h are simple, can you prove this? The g you can write it as sum of weighted sum of indicators, h also you write it as a weighted sum of indicators, and you can from the definition itself you can verify that this is true, right. For simple functions this is very easy. Okay. Now, going beyond simple functions, the next step will be to look for prove this for non-negative functions which are not necessarily simple, right. So, that is very difficult to do if you take the supremum definition I gave. Okay. So, one of the things about say there are a couple of ways of defining the integral. The way we defined it 6 of the 8 properties turn out to be very easy, or 7 of the 8 properties turn out to be very easy, but linearity turns out to be very difficult to prove using the supremum definition. What we will do therefore is we will prove monotone convergence theorem, which is a very important theorem in integration theory, and then get back to proving linearity, alright. So, because the definition we gave is conducive for proving many other properties, but it is not very conducive for proving linearity. Okay. So, we have to take a slightly difficult route through this fundamental theorem called monotone convergence theorem, which we will do later, actually we will do very soon, maybe next lecture. Alright. So, I will only say that this is easy to prove for simple functions, non-negative functions and more general functions we will get back later. Okay. Let me not worry about proving this, and similarly for random variables this is always true as long as all the expectations are well defined. Okay. Again the proof will be along the same lines, you prove it for simple random variables and then use monotone convergence theorem to prove linearity. So, this is expectations are linear no matter what else is true. Okay. X and y need not have any further structure to them. Okay. X and y may be have any joint CDF whatsoever, they may have different marginals, they may have any joint distributions whatsoever, they may not be independent or any such thing, right. It is always true that expectation of x plus y is equal to expectation of x plus expectation of y, and similarly this generalizes to any finite sum, right. If you have a finite sum of g 1 g 2 g n, you can always write it as the sum of those n integrals. Similarly, if you have n random variables, expectation of x 1 plus x 2 plus dot 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 x n is equal to sum of the individual expectations. True for finite. Okay. I am not saying about if this is finite, if the number of terms you are summing is finite, this is always true. Okay. That is very easy, because if you have x plus y plus z, you can write this as x plus y plus z and invoke the same thing, right. Any questions on this? We get to the proof later. Okay. Scaling. So, this is scaling property of integration. So, you can this just says that you can bring the constant out of integration. This is something you have been doing all along, and it is true for abstract integrals as well, right. And similarly for random variables, so expectation of So, if a is greater than or equal to 0, expectation of a x will be equal to a times expectation of x. Okay. How do you prove that? There is only one way to prove things, right. So, you start off with simple functions again, you take that g is equal to a weighted sum of indicators and write out. So, a g will also be a simple function, whenever g is simple a g will also be simple, that is because I have assumed a is bigger than or equal to 0, right. So, and then you write that integral out and then you verify that you write that integral out and verify that they are equal, right. It is a very trivial exercise in. So, for simple functions it is easy. Now, for non-negative functions, so for non-negative functions you have to apply the supremum definition. So, the way it works is this. So, a equal to 0, the result is obvious, they are both 0, right. So, let us assume a bigger than 0. Okay. So, proof assume a bigger than 0. Clearly, if q is in S of g, then a q is in S of a g, correct. Actually, it is not just clearly, so it is actually if and only if, as a matter of fact, correct. What does that mean? What does that mean? So, any simple function q which is less than or equal to g, right, if this is the case, then a q is a q is a simple function less than or equal to a g and vice versa, right. So, that is very clear, right. So, now you apply the supremum definition. So, you have integral a g d mu, right. So, I have to be a little bit careful here. So, I have to look over the supremum of all q, let us say q prime in S of a g, is not it, of integral q, well, q prime d mu, is that right. So, that is by definition. See, but this q prime is a q for some q in S g, correct. So, I can write this as supremum over q in S g integral a q d mu, correct. Maybe I am skipping one step, you can write it as a q belongs to S of a g, right, and then write the same thing, right. So, is this okay with me? So, now what happens? So, this is a simple function now, right. For simple functions I can bring the constants out because you can explicitly prove that to be the case, right. I can bring the constant out here, right. Can I bring it out here? I eventually have to bring it out here, right. So, bringing it out here is not a problem, but since a is non negative I can bring it out here as well, correct. So, that is equal to supremum. So, supremum q belongs to S g a integral q d mu. This is because q is simple, right. Now, this A is non-negative. So, the supremum of that set of numbers will be the same as A times the supremum of that, right. So, this is equal to A times the supremum of. So, this is because A is non-negative. Okay. Q belongs to S G integral q d mu, and this is equal to A times integral g d mu, correct, by definition. Okay. So, I hope this is correct, right. I mean, look over this argument very carefully. It looks like everything is obvious, but each step requires a little bit of thinking, right. You have to be careful in writing this down. Okay. Yeah, so this comes out because of q is a simple function, and the A eventually gets out of here because A is positive. Okay. All right, great. So, I think I am done with properties. Yeah, so I am done with the basic. So, the elementary properties of integration I am actually done now. Okay. So, the properties that remain are the more fundamental theorems of integration, right. So, we will do, actually there is just one fundamental theorem, and that is the monotone convergence theorem. The monotone convergence theorem, which is regarded as the cornerstone of integration theory, and if there is one theorem in integration theory which is which is the single most important one, it is clearly the monotone convergence theorem. We will also do dominated convergence theorem, which follows as a corollary to monotone convergence theorem, and there is also a result, a very well known result called Fatou's lemma. Okay. That is a result I will mention, but not prove. Okay. It is not included in your syllabus. Okay. But monotone convergence theorem and dominated convergence theorem are very useful in practice, and they are very important theorems. So, I will those we will do in proper detail. Okay. Before we get into that, so I think there is one little unfinished business from the past. If you remember, I mentioned something called the inclusion exclusion principle for probability measures. Remember what that says? It says probability of A union B is probability of A plus probability of B minus probability of A union B, and similarly for n such events. If you have union over n events, you have to pull out the intersection, add back intersections, and so on, right. Remember that formula. So, what I said back then when I was dealing with properties of probability measures was that you can prove it using induction, right. It is true, you can prove it using induction, but now that we have done expectations in integration, there is a very straightforward proof of getting the inclusion exclusion principle. So, those of you who actually bothered to write down the induction proof will probably know how messy it was. It's doable, there is no intellectual challenge in it, but it was you have to sit down and do it carefully, right. It is a very messy exercise, but we will see that using indicator random variables you can prove the inclusion exclusion principle very easily. Okay. Let me just indicate that right now. So, inclusion exclusion principle. So, inclusion exclusion formula if you like. So, recall. So, this is from your first chapter. We said that probability of A I is equal to sum over I equals 1 through n probability of A I minus sum over I less than j probability of section A j dot minus, so plus minus 1 to the n minus 1 probability of intersection. So, this is the inclusion exclusion rule, right, just recall this from memory, right. So, you have to add all the probabilities, subtract the probabilities of intersections 2 at a time, add 3 at a time, subtract 4 at a time, and so on, right. So, in order to prove this, so I am going to prove this, okay, and I am going to finish it here, okay. This is all the space we will take, okay. So, you will agree with me that indicator of this set. So, I am looking at the indicator of that event. Okay. So, this is the indication, this is the indicator of that at least one of the AIs occurs, one of the A1 through AN occurs, and that is equal to 1 minus the indicator that all the AIs fail to occur, correct. So, this is the indicator that all the AIs fail to occur, 1 minus the indicator of that is the indicator of at least one AI occurring, right, this you will agree, right. Now, what is the indicator of, so what is the indicator of A intersection B? The indicator of A times indicator of B, correct. Indicator of A intersection B is indicator of A times indicator of B. So, this can be written as 1 minus the indicator of, well actually let me write this as product indicator AI complement I equals 1 through n, right. Now, indicator of AI complement is 1 minus indicator of AI, right. So, I am going to write this as 1 minus product one minus indicator AI, agreed with me so far. Now, one more step is all that is needed. So, you have to go from indicator to probability. How do you do that? So, how do you go from the indicator of event to the probability of event? Take expectations, right, because indicator of I of A is equal to probability of A, correct. So, you take indicator of this, what happens? You get this, correct, and then you have to take expectation here, right. So, what will happen here? So, if you expand this out, so the 1 will there are a bunch of 1 minus terms here, right. So, the 1 will hit with this the first one here. So, if you expand this product out, what you will get is you will get a sum of the indicators, right, minus you will get indicator AI, indicator AJ, right, all the IJs. You will essentially get terms like this, you take expectations, you will get this, okay. So, you expand and take expectations, that is it, you are done. Expand out and take expectations, right, and you will be done, okay. So, in order to write it, maybe it will take a little more space, but I am sure you can do that, right. So, you just expand this product out, this is like 1 minus these indicators, this will be 1 minus IA 1 minus IA 2 so on, and then there will be 2 terms 2 at a time, 3 at a time, and so on. Finally, there will be a product of minus 1 to the n minus 1 indicator of all the product of the indicators of all the AIs, which will finally give you that term. Finally, if you take expectation, you get that term, okay. So, this is a very simple proof of inclusion exclusion principle, okay. Actually, this is the most transparent way to see why this inclusion exclusion principle is even true, right. The induction proof, while it is a mathematically correct proof, it gives you, does not give you much more intuition about what is going on, right. This gives you a very structural intuition on why this inclusion exclusion principle is true. Are there any questions? If there are no more questions, we will start discussing monotone convergence theorem. Okay. Maybe I will not finish discussing today, but we will start off discussing what it is about. Okay. So, this monotone convergence theorem, as I said, is probably the most important theorem in all of integration theory, all right. So, the monotone convergence theorem, qualitatively what does it do? It just gives you a way, gives you conditions, a condition rather, under which you can interchange limit and integral. Okay. So, normally if you have limit n tending to infinity integral f n, you have a sequence of functions f n. Okay. Let us say you have integral f n d mu, right, or you can think of it as integral f n dx if you like. If you just want to think of integrating on the real line, you probably know that you cannot always integrate interchange in limit and integration, right. So, the limit of an integral is not always equal to the integral of a limit. We will see some examples. Okay. But the monotone convergence theorem says, gives one sufficient condition under which you can interchange limit and integration. Okay. Namely, you can say that the limit of the integral is same as the integral of the limit function. So, in particular, if f n converges to some function f, integral of f n need not always be equal to integral of f. Okay. In particular, the monotone convergence theorem says, if f n converges to f in a monotone way, right. Suppose f n monotonically increases and converges to f, or f n monotonically decreases and converges to some f, then you can interchange limit and integration. Okay. So, in that case you will in fact have that integral limit of the integral is equal to the integral of the limit. Okay. So, that is what the monotone convergence theorem says. Okay. It is actually to state it is fairly simple. Okay. But before I state this properly, I want to define some concepts on convergence of functions. Okay. Let f n from omega to r, this could actually be r union plus or minus infinity as well, okay, be a sequence of measurable functions. Definition: we say f n converges to f is another function from omega to r, okay, r the real line. We say f n converges to f pointwise if for all omega in omega f n of omega converges to f of omega. Okay. So, pointwise convergence of function is a this is what this is it means, right. You fix an omega in the sample space in your set omega, and for every omega f n of omega will be a sequence of what? Fix an omega, f n of omega is a sequence of real numbers, well not including plus minus infinity, not quite real numbers. So, this is a sequence, let us just say it is a sequence of real numbers. If it is true that that sequence of real numbers converges to this real number f of omega, and if this holds for every omega in omega, then we say f n converges to f pointwise. Okay. This is clear. So, these f n's, so this could be a sample space, this could be random variables for example. Okay. F n's could be x n's, some random variables, and in that case you say that random variables x n converges pointwise to x if for every omega in the sample space x n of omega converges to x of omega for example. Okay. Now, it remains to be well, the one little thing that I have not really spoken about is that if you have a sequence of functions converging pointwise, the limit function is also a measurable function. Whenever these f n's are measurable, the limit function is always a measurable function. Okay. This is something that can be proven. Okay. I have not done it in class, but it is always the case that if you have a sequence of measurable functions converging pointwise, then the limit is always a measurable function. Okay. This can be proven. So, is the definition clear? And then I will just put one more definition which is closely allied. Let us say that, so omega, let me say that omega f mu is my measure space. Okay. So, omega is this guy and I have f n mu on that space as well. We say that f n converges to f mu almost everywhere if, what do you suspect it is? What do you think this will mean? This convergence holds not necessarily for every omega in the sample space, but instead it may fail to hold on a set of mu measure 0. Okay. If f n of omega converges to f of omega for all omega except perhaps on a set of mu measure 0. Okay, this is also a definition. So, this is a slightly weaker definition than this. Okay. This is saying that for every omega in omega you need this convergence f n of omega converging to f of omega. Here you relax saying, oh maybe it is not always true that, so it is not true that for every omega it holds. There may be a few omegas or a countable set of omegas or some mu measure 0 set of omegas, right, some small set, right, some there were 0 measure set where the measure is mu, right. On that set you do not have convergence or you may not have convergence, right. You can't quite say what f n of omega is doing on a 0 measure set, but outside that 0 measure set you have convergence. In other words, there is a set A, a subset A of omega which has full mu measure where convergence happens. Okay. So, in the context of probabilities, this has a very important interpretation which we will come to a little bit later again. So, this will become almost sure convergence of random variables. Have you heard that term before? Almost sure convergence of random variables. So, there we have a sequence of random variables x n. You have x n of omega converging to x of omega, not necessarily for all omega in the sample space, but on a set of probability 1, right. There may be 0 probability omegas where the convergence does not happen. Okay. So, this is almost sure convergence when you are talking about convergence of random variables. Okay. I will write that down explicitly a little bit later when we study convergence of random variables. Okay. Okay, so far okay, the definitions everybody fine. See now, so here, so this is pointwise convergence, right. Now the issue is if you have a measurable function converging pointwise to f of omega is always measurable. Now the question is if you integrate f n d mu, right, if you integrate f n d mu you get some sequence of numbers, right, integral f 1 d mu will be some number, integral f 2 d mu will be some number. So, integrating f n d mu gives you a sequence of real numbers, right. Now, the question is does that sequence converge at all, right, that is question number 1. If it does converge, does it converge to the integral of f d mu? Okay, that is the question we are trying to address. Okay. The answer is no, generally that is not true. Even if you have convergence of f for every omega in omega, it is not true that integral f 1 d mu is equal to integral f d mu, not true. Okay. So, the question we are trying to answer is this: can we interchange limit and integration? See, that is the colloquial question, right, i.e., if let us say f n of omega converges to f of omega pointwise, is it true that integral f n d mu converges to integral f d mu? Okay. Answer is no. Okay. So, what I am saying is, so rather so in another way of writing is, if you want to write it more explicitly, is it true that the limit of the integral is equal to integral of the limit function? Okay, if this is a little more explicit, you can take this. Okay, it is not true that this is not true. Okay. To see an example, I will just conclude with an example. Let us say you take, let my omega f p be my favorite 0 1 integral 0 1 interval endowed with Borel and Lebesgue measure. Okay. That is my probability space. I want to define f n of omega is equal to n for 0 less than or equal to 0 less than or equal to omega less than or equal to 1 over n, okay, or less than 1 over n, okay, and 0 otherwise. Okay. So, that is my So, that is my sequence of functions. So, f n of omega will look like that. So, if I plot it, so everything is in, all the action is in 0 1 interval. Okay, this is 0 1 interval. So, f 1 will be 1 in 0 to 1, f 2 will be 2 in 0 to half, f n will be n. So, this will be 1 over n, solid dot here, 0 everywhere here, hollow dot here, right, solid dot here. Actually, it does not matter what the, here it is a hollow dot, here it is a solid dot. The functional value is n. Okay. Here you will see that, so if you want to, so integral, what is integral f n d lambda? So, I am going to integrate f n with Lebesgue measure. Okay. Integral f n d lambda will be equal to 1, for all n this is equal to 1. On the other hand, if you look at the limit function, so the limit function f n will be, so for all omega lying, so for all omega that is strictly bigger than 0, the limit function will be 0, correct. At 0 the function will be plus infinity, actually because I have put a less than or equal to here. Actually, if I put a, so if I put a strictly less than here, the limit function will in fact be 0 everywhere, right. But yeah, I mean, so if you like, so to avoid confusion, let us just take this. Okay. So, let me just put the function at 0 here, okay, just avoiding confusion. So, let me do that, and at 0 it is 0, the function is 0. So, the limit function is equal to 0 for all omega and omega, correct, because you give me, no matter which omega you give me, there will be some n beyond which the function is 0, right. So, the limit function is identically 0, correct. So, if I look at f defined as limit f n, this is 0 for all omega, and integral f d mu will be equal to what, 0, right, and this is not equal to 1, right. So, integral f n d lambda is equal to 1. So, this implies limit n tending to infinity integral f n d lambda is also equal to 1, right. So, this integral is always 1. So, the limit is 1, the limit of the integral is 1, but the integral of the limit is 0. Okay. So, it is clearly not the case that you can blindly interchange limit and integration. Very simple example says that you cannot do it, right. So, I made this strictly lesser. So, even if this was less than or equal to, the limit function will be 0 for all positive omega, and it will take the value plus infinity at only at 0, okay. And because it is a function that is 0 almost everywhere, integral of a function which is 0 almost everywhere is 0. So, it would not have mattered even if I had less than or equal to here, there will just be one point where the function is plus infinity, but that one point has measured 0. So, there is no difference, okay. Is that clear? So, you cannot interchange limit and integration. So, what we will see next is, next class I will state the monotone convergence theorem, which says that if this limit were to be a monotone limit, if f n converges to f monotonically, then it is always the case that you can interchange limit and integration. So, in this case monotonicity does not hold, right, because f n will look like this and f n plus 1 will look like that, right. So, it is not true that they are monotone in n, right. So, we will see this next class.